Hello everyone, welcome to week 6 of the massive open online course, our 15th iteration for the master's degree in digital currencies at the University of Nicosia. I'm Andreas Antonopoulos and I'll be your teacher for this session. Now we are covering various types of blockchains today. We're talking about permissionless and hybrid solutions of blockchains, as well as different forms of consensus that may occur. We will be discussing more of that next week in week 7 when we talk about consensus algorithms and alternative consensus algorithms such as proof of stake, but we do have some questions this week about proof of stake also. So I'll split some of my time between this week and next week talking about consensus algorithms. Let's start with a question from David. David asks, what is proof of stake? How does it work? How is it better than proof of work? David, proof of stake is a consensus algorithm where validation and security is provided by participants who, as a bond, as a guarantee of their security work, deposit currency on the blockchain instead of burning energy as in proof of work. So in proof of work, the guarantee that the miners are doing the work and validating the security of the chain is in the form of energy consumed, and that energy has a cost which the miners cannot recuperate unless they do the validation correctly and get rewarded. In proof of stake, what is being consumed as a guarantee is the currency. So what happens is, let's say you have a proof of stake blockchain called Andreas coin. And in Andreas coin, holders of Andreas coin will deposit an amount of Andreas coin onto the chain that gets locked into some kind of smart contract or as part of the consensus algorithm, and they validate against that. So they provide that as a guarantee that they'll do the validation. Effectively, they then vote by signing on specific blocks as valid. Now, if those blocks are considered invalid by the rest of the network, they may end up receiving a penalty, and that penalty is called slashing. Slashing is a mechanism used in proof of stake where those who put their stake, the amount of currency that they guaranteed, lose some of it, perhaps even all of it, because they didn't validate a block correctly according to the consensus rules. If they do validate it correctly, they receive a reward, just like in proof of work. So we have a number of staking systems today that already exist. Their proof of stake coins have been running for a very long time. In fact, if you look at the history, proof of stake was invented before proof of work, meaning that proof of work was invented by Satoshi Nakamoto in order to compensate for what was seen as weaknesses in a proof of stake system. There are a number of ways you can look at proof of stake versus proof of work, and of course this is a very controversial and opinionated subject. Answering the question, what is better? Is proof of work better than proof of stake, or is proof of stake better than proof of work? Really implies that there is an objective measure that can be applied across all different use cases of a blockchain and give us an answer. The problem is that, in my opinion, there is no objective measure. Each of these systems has advantages and disadvantages. And so which of those advantages and disadvantages are appropriate or relevant to your use case will determine whether you consider proof of work or proof of stake better. Meaning that the best way to answer that question is better for what? If you say proof of stake is better for X, then we can make an evaluation if the trade-offs involved in proof of stake are better for application X or not. Objectively, you can't really compare the two because they simply have different trade-offs. So they are qualitatively different as well, meaning that proof of work suffers from different weaknesses, if you like, or vulnerabilities or attack scenarios than proof of stake. It has different downsides, but it also has different upsides than proof of stake. So common criticisms of proof of work are that a consortium of miners can attack it using a 51% attack, or that miners can become concentrated in areas where chips are manufactured, such as China, or that proof of work uses a lot of energy. What are the advantages of proof of work? Well, proof of work allows nodes to participate in consensus without external authority. That means that a node can join a proof of work network and be able to validate from the initial genesis block, but also be able to validate even with some recent blocks and know that they are on the correct chain because the proof of work itself demonstrates long-term immutability. In proof of stake, one of the weaknesses is what's called a long-range attack, meaning that you cannot make the past immutable against attack because if miners collude to go back and remine the chain far enough back, they can effectively undo the effects of the penalties, the slashing penalties, and they can agree on a new reality. So in proof of work, if all of the miners collude, they can't change the past without actually expending the energy. Whereas in proof of stake, if miners collude, they can change the past. Of course, the community can resist that by checkpointing. And this is called subjectivity. So you can say, well, no node needs to validate things in a complete vacuum. They can validate by looking at what the rest of the community has considered a valid chain and refuse to accept answers from consensus that violate that. So you have effectively a reference point that depends on what the community considers the truth, subjectivity. In the case of the Bitcoin blockchain, you don't need that, but you pay a big price in order to not need that. So then the question is, how necessary is that? And what exactly does it protect you against? And depending on how you see that question, you may decide that proof of stake or proof of work is better for your particular application. Now, my opinion is that proof of work provides a very robust defense against certain types of attacks that are likely to involve state-level actors. So it prevents those types of attacks and provides a very robust form of immutability, which is particularly useful if what you're trying to do is create censorship-resistant, robust, sound money. But do you really need it for a smart contracts environment? Probably not. And in fact, because it's very expensive in terms of energy, maybe we can only afford one of those, and we can use that to offer effectively a strong degree of assurance for other proof-of-stake networks through a process called checkpointing. So we may only afford one proof-of-work network, and that might be enough for the whole planet. But again, that's just an opinion. So we don't know the answers to these things yet. We're going to find out as proof-of-stake networks and proof-of-work networks are subjected to adversarial conditions and operated at scale with lots of money at stake, no pun intended there. And the end result will be that we will find out what kinds of attacks they can resist and what kinds of attacks they cannot resist. The good news is that this offers us a glimpse into the broad variety of consensus algorithms that are out there and how the research in this area has developed dramatically in the 12 years since Bitcoin was created. There's a follow-up question in the chat that I see. GeekPie100 asks, why is Ethereum planning to switch to proof of stake? Well, that is really a matter of design philosophy and principles, but Ethereum isn't planning to switch into proof of stake now. Ethereum was always intended to switch to a proof of stake system. However, in order to bootstrap a proof of stake system, you need either a pre-mine or an early proof of work, or both. You can't have a scenario where you start with proof of stake and that's your primary mechanism for distributing the tokens, because then you start off with a situation where the control of the consensus algorithm is very, very concentrated. So Ethereum was always heading to proof of stake. It's baked into the design of the protocol. And in fact, there's a mechanism in there to force continuous change. Whether you agree with that mechanism or not is besides the point, but it was put there for that reason. And that is called the difficulty bomb, that basically continuously causes difficulty to escalate and requires it to be diffused by hard fork changes to the protocol. This ensures that the protocol cannot get ossified under the control of the proof of work miners, and the developers do have an opportunity to steer it towards a proof of stake network, meaning that if the miners decide we don't want to do proof of stake because it's not in our interest, we want to stay on proof of work, well, that is untenable, because in the long run that proof of work gets harder and harder and harder, and then you need a hard fork to change it, and that hard fork gives the developers an opportunity to change the consensus algorithm. At least that's the theory. All right. Wendy asks, as a follow-up again, what does it mean to stake your Ether? So what it means to stake your Ether is that you are running a node that contributes at least the minimum stake of Ether, which is currently 32 ETH, into the ETH2 network, the beacon chain, and then validates the beacon chain in order to maintain that stake and earn a reward. Now, if you do that, as far as I understand it right now, you are locking in that Ether into the staking contract, and you will not be able to get it out of that staking contract until ETH2 launches its full capability, which might be 2 years. So you are committing to maintain that stake in the beacon chain, and then you need to validate the beacon chain, which many people do through an intermediary, through, for example, an exchange that is staking their Ether for them and running validation nodes in ETH2 in order to earn rewards on that stake. Because now ETH2 is a very forgiving proof of stake algorithm, because the slashing penalties are very lax. You can be offline almost 50% of the time and not get slashed. The participation requirement is fairly low, and it's designed to decentralize that proof of stake algorithm as much as possible, but you can still get slashed, and there are risks with doing this, and mostly at the moment the risks come from software vulnerabilities, bugs basically in the code. So if you have a buggy client, you can end up getting slashed through no fault of your own because your client didn't validate things correctly, and in fact that has already happened. So what does staking in ETH2 mean? It means that you deposit 32 Ether from the Ether1 chain, ETH1 chain, the Ethereum 1 chain. You deposit that into a smart contract, and it gets bound and staked into the beacon chain of ETH2, and then you have to run a validation node in order to protect that stake and earn reward on it. And if you don't do that correctly, you can lose some of your staked Ether. So it's a fairly risky thing, but it also gives people an opportunity to engage with the validation mechanism and develop their skills over the long run in maintaining these validation nodes, which is one of the reasons I'm actually running a validation node and trying to get involved in the ETH2 validation so I can learn about it. All right, let's see. We have a couple of questions about Ethereum's nature, which is we've discussed public permissionless blockchains versus permissioned blockchains and private blockchains in this week's session. So the question comes from Claudio. Claudio asks, is Ethereum really public and permissionless? Many people use the DAO attack story and the consequent rollback as a way to prove the biggest difference with Bitcoin. The fact that there was a rollback, that few people, including the creator Vitalik, were able to hard fork and roll back the chain, is a fact that should highlight the big risk with Ethereum. If something similar would happen to Bitcoin, the value of Bitcoin would probably drop by a lot. What is your opinion on this? I don't really see this as a good faith argument. And the reason I don't see this as a good faith argument is because the design principles and community principles of Ethereum are different from those of Bitcoin. Ethereum very, very explicitly has as part of its design principles and its methodology a culture of moving fast and making changes even if those changes increase the risk. So in a smart contract environment where you have Turing-complete smart contracts that are trying to iterate to maturity, you need to do more iterations, you need to take more risk. This allows the protocol to move forward and innovate fast, which you need in that kind of environment. So if Ethereum took the same conservative approach as Bitcoin development does, Ethereum wouldn't be able to actually explore the application space that it's exploring. It wouldn't be able to develop the things that it's developing. In order to develop the things that it's developing, it has to be a more risky environment, a more experimental environment with a lot more flexibility. That is an explicit design trade-off in the fundamental design of Ethereum. That means that people who operate in the Ethereum space should understand that sometimes things can go wrong in a spectacular fashion. That's one part of the story, which is that don't expect Ethereum to behave culturally or from a design perspective, from a design principle, like a hard money conservative chain that Bitcoin is. That's not its goal. It never was its goal. And you may think that that means that it's doing things wrong, but just because it's different doesn't mean it's wrong. Wrong for what? Again, this is the same discussion as what is better. If what you're trying to do is build sound money, then clearly conservative development is better for that application. But if what you're trying to do is Turing-complete smart contracts with the types of goals that Ethereum is trying to fulfill, then conservative development actually undermines that. So what's best for Ethereum isn't best for Bitcoin and vice versa. And you know, if you're making the assumption underlying this type of question, doesn't really say much about Ethereum or Bitcoin, but it does say a lot about what you think the correct application or useful application is and what you think the not useful application is, which of course you're entitled to that opinion. There is one little other thing, which is if something similar would happen to Bitcoin, the value of Bitcoin would probably drop by a lot. Well, hang on a second, because something similar did happen to Bitcoin twice. We have two examples. One example which was a hard fork, and the other example which was a rollback that did happen to Bitcoin that effectively happened at a about the same point in the life cycle of Bitcoin that perhaps you don't remember, but they did happen. And in fact, they didn't cause Bitcoin to drop by a lot any more than the DAO ended up, I mean, sure, it set back Ethereum by a couple of years, but it was able to overcome that. And in fact, we saw that Ethereum Classic didn't, in fact, provide a better alternative. So let's look at what happened in Bitcoin. In Bitcoin, we had the inflation bug, where I believe it was something like 1.5 billion Bitcoin was mined in a single Coinbase transaction. Now that block no longer exists, and the reason it no longer exists is because the code was changed, that block was rolled back, and it's as if it never happened. And that required centralized coordination by developers and miners to change the code of Bitcoin and roll it back. Then, in April of 2013, a bug in version 0.8 of the Bitcoin core software caused effectively a open file descriptor overflow in all 0.7 clients, causing a fork in Bitcoin that ended up having a 26-block divergence between two different versions of the chain, which then required an intervention by developers and miners to roll back everything and do a 26-block reorganization. So it did happen in Bitcoin. And in fact, a hard fork has happened in Bitcoin as well with the emergence of Bitcoin Cash and SV and 40 other forks. So these things have happened. There is a fundamental difference between the conservative culture of development in Bitcoin, which has its advantages and disadvantages for the use case of Bitcoin. The advantages are that it's much harder to do a social attack on the developers or to make dangerous fundamental changes to the protocol that undermine its value proposition. The downside is that Bitcoin has a tendency towards ossification of the protocol, where it becomes more and more difficult to make changes, even changes that are broadly supported by the community. A perfect example is SegWit, but an even better example is the current change, Taproot, where the debate about how that should be activated, even though it's very strongly supported, has effectively devolved into a dead-end argument, and now we're looking at problematic activation of Taproot. That is a direct result of the conservative culture of development in Bitcoin. So the things that protect Bitcoin from takeover also prevent Bitcoin from evolving as fast. And that may be a good thing, or it may be a bad thing, depending on what you think of its pace of evolution. Those things are very different in Ethereum for good reason. A similar question, it comes from Mario. Mario asks, at first glance, the change in Ethereum blockchain in 2016 to roll back the 50 million loss by hack appears to indicate some control and centralization of Ethereum. I would appreciate if you would briefly summarize how consensus was reached among the majority of Ethereum's users and developers, which created the two separate hard forks, ETC and ETH, and whether this consensus mechanism for ETH is considered as proof of a decentralized ideology. Here's the thing. In the case of the DAO rollback, the consensus in the community was reached through a variety of mechanisms. There was discussion among the core developers of Ethereum, a lot of debate. There was a lot of debate that happened on social media. There were various stake-based voting systems that were put into effect, where people voted with their Ether in order to signal their support And you know, all of these debates at the end of the day come back to the fundamental issue of how do you achieve consensus in a Byzantine fault-tolerant system where Sybil attacks are possible. So this goes back to week 1 of our conversation. How do you agree what the community wants? So the answer in a proof-of-work system is the miners vote with hash power. The problem with that is that it gives too much power to miners. So then you have to have a debate among developers. But how do you know how developers are inclined, and how do you measure that? How do you measure the consensus among node operators or users? And this runs into a lot of problems, because almost immediately people try to build consensus measuring mechanisms which are not proof of work, which are not proof of stake, which are not the consensus algorithm. So, for example, we saw this with SegWit, we saw it with the DAO, we're seeing it now with Taproot. And this takes us back to the same fundamental question, which is how do you achieve consensus across a Byzantine fault-tolerant system where the debate is not just happening on the Byzantine fault-tolerant system and the voting is not just happening there. So how do I measure, for example, how many of the Ethereum nodes want to do this DAO fork? There is no mechanism to do that. It's the same problem with how do I measure how many of the actual Bitcoin nodes wanted SegWit or not, and how many of the Bitcoin nodes want Taproot or not. And you can say, well, they can signal, or they can set up rules, or they can do a user-activated soft fork, or they can vote by including something in their headers. The problem with that, of course, is that you can bootstrap 10,000 nodes on different IP addresses by using cloud services, by using data centers, if you have the resources, by even taking over a botnet and installing this on unsuspecting Windows 95 users all across the world who haven't upgraded their desktop. And that's called a Sybil attack. So how do you measure that? So Ethereum had the same problem that we see in Bitcoin, that we see in every other chain, which is when you're trying to resolve issues that lie outside of the consensus, meta-consensus problems, consensus about the consensus algorithm, consensus about how the consensus algorithm should change. You can't use the consensus algorithm to do that, because the people who are invested in the consensus algorithm can deadlock that process. If it makes sense, in the case of the DAO controversy, the problem is that you have 3 broad constituencies that have interests here. You have miners, who have interest in preserving the consensus algorithm as it is because they've built their business infrastructure around that. Then you have the developers, and the developers who are writing the software, obviously, they want their software to be used by the broadest number of users and validated and secured by the largest amount of hash rate, but they have their own interests too. And then you have the users, including the users who are victims of the DAO hack and therefore would like to see their money back, and users of Ethereum who are not victims of the DAO hack and see the possibility that the DAO hack actually benefits them. It benefits them by reducing the immediate supply and availability in the economy of that money. And they don't see why they should endanger the value of the currency by rolling back to make whole those who were victims of the DAO hack who took a risk and then lost. Why should they get a bailout? That's exactly the debate that happened. But how do you measure the consensus or agreement of these 3 distinct communities without falling victim to Sybil attacks, without creating environments where you're either getting bias reflected in the decision, because that bias has to do with different motivations and interests, conflicting interests, or that bias is then further amplified by cheating, basically, by Sybil attacks, by people voting multiple times, either through a staking mechanism. So let's say you vote by the amount of Ether you have or are willing to put in. Well, the participation of that is always a very, very small participation among the broader community, because only those who have the technical capability to participate in that vote and who have their own keys, kind of first-class citizens, if you like, of the blockchain get to vote. All of this to say, it's very difficult to actually do this. And I think from my experience of watching the DAO vote, I think that in the end there was overwhelming consensus to roll back the chain and fix this. And there were a number of reasons that was a motivation, including the recognition that if you go to a proof-of-stake system and 14% of the entire stake of Ether is now owned by a malicious actor, then that causes problems in the future. The other one, of course, being that it creates a moral hazard, because people are more willing to risk their money if they think they're going to get a bailout. And I think the end decision was a bit like the 2000 Florida election, which was, listen, in this particular case, we're going to change the outcome, but this case will not be used as a precedent for future changes, meaning we're not going to give you the moral hazard, or we're going to try to avoid the moral hazard by saying this time we're going to bail out because this was a one-off unique scenario that will not get repeated, and one of the reasons it won't get repeated is because we're telling you now it won't get repeated. And of course, some people didn't agree with that, and they were free to fork off and create ETC, which didn't do a rollback. Is this decentralized? Well, I mean, the decision was very decentralized. And it was decentralized in the best way, primarily because anybody who didn't like it could effectively fork and do both. So one of the things that actually enables decentralization is the ability to fork. And it seems counterintuitive. It seems counterintuitive because if you fork, doesn't that violate decentralization? No, it doesn't. Basically what it says is, if the choice is between A and B, the answer is A and B. Not A or B, but A and B. And as a participant, you can keep your money in both and see which one works. So that allows the market to decide which is the most decentralized way of deciding. Effectively, the decentralization in this case came not only from the fact that many different opinions through many different measuring systems were used, but that fundamentally the market gets to decide whether immutability is valuable in the context of the application use case of smart contracts. And I think that's a very different decision in that case than some other use cases. If you think, for example, that the DAO demonstrates that no blockchain is immutable, I would argue that in a different scenario, a different outcome would have occurred. You cannot draw those kinds of decentralization broad conclusions. Wolfgang, for example, says, the ETH fork destroyed my trust in immutability of blockchains. To me, I understand why you are saying that, Wolfgang, but to me that is drawing a generalized conclusion from a particularized circumstance. Let's say that there was a faction within Bitcoin that said, let's change the 21 million limit and increase it. Now, that faction could create a fork And in that fork, they could have, you know, the Hitchhiker's Guide to the Galaxy Bitcoin that has 42 million coins, not 21. And so if they had, you know, HGTTG coin, that one would have 42, Bitcoin would still have 21. Did that change the immutability of Bitcoin? No. It didn't change the immutability of Bitcoin any more than any of the other 40 forks of Bitcoin changed the total supply of Bitcoin. It didn't. And what is Bitcoin? Bitcoin is whatever you want to run with your consensus rules, and no one can force you to change what you run with your node. So this is a difficult topic, and I understand why it caused a lot of confusion. Bottom line, does the DAO attack and subsequent rollback mean that Ethereum is not decentralized? No, I don't think so. I think it shows that given sufficient consensus, and there will always be a splinter group that disagrees, you can, in fact, roll back something like that at least once. Who knows if it will ever happen again or if it can happen again. And if you think that immutability is so important, you have the choice of instead investing your time, attention, passion, creativity, and smart contract investments in Ethereum Classic. So you have both choices if you want, and the market gets to decide which choice was more important. And just because the market decided one way this time doesn't mean it will decide it the same way next time. And the other part of the question was, does that mean that Ethereum is or isn't permissionless? Does that mean that Ethereum is or is not a public blockchain? And to me, that is very, very straightforward. Ethereum is absolutely permissionless and absolutely an open public blockchain. It just has different characteristics than Bitcoin. Bruno asks, how easy is it to make a 51% attack in Ethereum, and how exactly does this work? Well, that depends. If you mean proof of work Ethereum as it currently exists, then it's exactly the same thing as in Bitcoin. Meaning that if 51% of the hashing power colludes, then they can do a 51% attack on Ethereum using the proof of work algorithm, just the same as they can do on Bitcoin. Now, there are some nuances there. There are some nuances that have to do with the Ghost protocol that Ethereum uses for its mining, where it's not a winner takes all. And so that's the greedy heaviest, I don't remember what the Ghost acronym means. 1 second. I'd have to look it up because I keep forgetting this acronym. I know, I should remember this, and I keep forgetting it. But in any case, greedy heaviest observed subtree. There we go. Thank you. So thank you, Google. Thank you, DuckDuckGo. Greedy heaviest observed subtree is the protocol that Ethereum uses to decide which chain wins. That's compared to Bitcoin's algorithm, which is the greatest cumulative difficulty chain, or sorry, greatest cumulative difficulty valid chain, which is the algorithm that Bitcoin uses to select the correct chain. The nuances of a 51% attack on Ethereum would be slightly different, but the overall strategic aspect would be the same. And it would be the same in other ways to Bitcoin's 51% attack. And it's important to understand this because this is a fundamental misunderstanding about 51% attacks and about blockchain consensus algorithms. If you have 51% of the hash power, you can mine all the blocks. But you cannot violate the consensus rules. You cannot change the consensus rules. You get to mine all of the blocks, which means you get to choose the transactions that get included in those blocks, which means that you can do a double spend attack, at least in the short term, until everybody turns up their validation level and stops trusting your blocks. You can also do a denial of service attack on the blockchain. You can stop processing transactions. Everybody's transactions, your competitors' transactions, some combination thereof. Or you can create such uncertainty that people stop trusting the transactions in the blockchain. So you can deny service. You can deny progress to the chain. You can effectively make the chain not function for transactions for the duration of your 51% attack, forcing a counter by developers in the economic interest of some sort, which may involve a change in the consensus algorithm. What you can't do is change the rules. A 51% attack doesn't make it possible for the 51%, or even a 100% attack with 100% of the miners colluding, does not make it possible to not prove that you did the work. You have to spend the energy and prove the work. Spend coins that you don't own by not signing. Not possible. Not validate signatures. Include transactions that are not valid. Produce blocks that have more reward than you should produce. Or invalid blocks in any other way that violate the consensus rules. A 51% attack does not make it possible for miners in Ethereum, in Bitcoin, in any proof-of-work chain to simply ignore the consensus rules. The same thing applies with proof of stake. And you asked about Ethereum, so I'm assuming you mean proof of work Ethereum. But if you were in proof of stake Ethereum, the percentages are different in terms of how many of the stakers need to collude in order to do an attack on a proof of stake algorithm. And it depends on how the proof of stake algorithm is controlled. Usually it's more like a 2/3 majority that you would need, not a 51% straight majority. But the bottom line is the same again. What can you do by engaging in a majority or supermajority attack against the consensus algorithm? You can deny service. You cannot change the consensus rules. And the reason for that is because economic actors or economically significant nodes that are validating transactions without mining but enforcing the rules on transactions that contain money that they care about will not accept your invalid transactions or blocks, which means that if you mine these invalid transactions or blocks, even if 100% of the miners agree that these are now valid, everybody else won't agree that they are valid, and therefore you will be mining a block that has no economic value. You will effectively fork. You will effectively fork, which means that even a 1% that mines valid blocks will now have 100% of the hash rate for the valid chain. And that 1% can be thwarted constantly by invalidating their chain. Again, denial of service. But you can't force others to accept an invalid chain or put their money on it. Or take your mining rewards or staking rewards and exchange them for products, services, or other currencies on marketplaces and exchanges. You cannot force others to give economic value to your attack coin. So it's very important to understand that a 51% attack is an attack against the consensus algorithm within the consensus algorithm. It doesn't give you the ability to depart from the consensus algorithm in any way other than creating a minority, economically unimportant chain that others will not consider valid. You can create a minority unimportant chain, but then everybody who is interested in the economically important valid chain will ignore you. And you can keep messing up their chain, but you can't force them to accept yours as valid. I hope that explains things a tiny bit. Let me check in the chat and see if there's any follow-ups on that. It's an important point. All right, there's a whole debate raging in the chat room, but it's not really related directly to what we're discussing here, so I will continue. Ethereum uncle block versus Bitcoin orphan block. This relates to something I just talked about. Vrakto asks, sorry if I mispronounced your name, Vrakto, can you explain the difference between the Bitcoin orphan block and the Ethereum uncle block? Is an orphan block still possible on Bitcoin's network? So a bit of terminology here because it's often confusing. The term orphan block isn't actually correct for Bitcoin. We call these stale blocks. They're called stale blocks because effectively they end up being on a chain that goes stale because it's not the chain that is extended. Meaning these are blocks that extended the chain in a direction that was not followed by the rest of consensus, and as a result, they end up being stale. They do not get included in the greatest cumulative difficulty valid chain. They're valid blocks on a valid chain, but they no longer have greatest cumulative difficulty, and as a result, they are considered stale. That means that their transactions never happened. Effectively, they're rolled back. And that also includes the Coinbase transaction, which means that if you mine a block, and someone else mines a block, and the rest of the network ends up extending the chain on their side, not the side that you extended, even though your block is valid and their block is valid, they're basically two children of the same parent. Your block is not orphaned. It is childless. I don't know if that makes sense. It has a parent. It has the same parent, and this is why the terminology is a bit confusing. They were called orphan blocks at a time, but that's not actually what it means. So if you mine a block here and someone else mines a block here, both of these blocks are valid and they have the same parent. They're siblings. And they're not orphaned because they have a parent, the same parent. But one of them keeps getting extended and the other one doesn't. Then as this chain gets greater cumulative difficulty, this block ends up being stale. It gets dropped. And this chain becomes the valid chain, the greatest cumulative difficulty valid chain, because it has more cumulative difficulty, more proof of work built up in that chain, which usually means also more blocks. So it's a longer chain. That stale block basically gets recycled. All of its transactions either are already in the other block or they go back into the mempool, and its Coinbase transaction never happened effectively, and the miner doesn't get the reward. Now, this is the fundamental difference between an Omer or uncle block in Ethereum and a Bitcoin orphan block. So Ethereum uses the greedy, heaviest observed subtree ghost protocol, which means that if there are other uncles, uncles because they are uncles to the children of their siblings, right? So this one got extended, so it has children. This one doesn't have children, but it is an uncle to this child. It gets a percentage of the reward of the parent. So the siblings share some of the reward, meaning that where Bitcoin is a winner-takes-all consensus algorithm, Ethereum is a winner-takes-most, but not all. And its siblings, the uncles of its children, do get some reward shared among them so that their work, since it was valid, is also rewarded. It's a different consensus algorithm. All right, we have a relevant question to this because this is a big part of consensus, and this comes as a common question. Mike Rosynth, or Microsynth, asks, what is the difference between a soft fork and a hard fork, and what kind of effect does it have on the original project? Now, people throw these terms around, and often they have colloquial uses that mean different things. But basically, the difference is whether these things are forwards compatible or not. Forwards compatible meaning if an unupgraded node from the past can continue to validate the chain or not. So if you do not change the software that you're running, after a soft fork, you can keep running that software and you will stay on the consensus chain. If a hard fork occurs and you do not upgrade your node to the new consensus rules, you cannot continue validating the consensus chain, and you will end up getting forked, meaning that you will drop off the majority chain and you will be on another chain, which may or may not have any continuity. It may continue to get mined or not. The DAO rollback was a hard fork, meaning that if you did nothing, right, you ended up forked. And if you wanted to continue to validate the chain under the new rules, you had to change your client. Effectively, Ethereum Classic was the do nothing and continue to validate, but with its own miners, because they had to also do nothing and continue to validate. Whereas Ethereum ETH was the forked chain that actually changed the rules by rolling back the DAO. With Bitcoin and BCH, it was the other way around. So BCH was the one that changed the rules in a non-forwards compatible way, meaning that it created blocks that the previously unupgraded nodes could not validate, whereas BTC could be validated by previously unupgraded nodes even after the SegWit change. So this is very, very confusing at first. If you want to understand it better, I did a complete talk on specifically this subject called forkology. And in forkology, I use the idea of a restaurant that caters to a vegetarian clientele. Let me explain. The fundamental difference between a hard fork and a soft fork is that a hard fork expands the rules, whereas a soft fork constricts the rules. So in a hard fork, things that were previously invalid are now valid. In a soft fork, things that were previously valid are now invalid. So the rules are narrowed. And I explain this by describing a restaurant. If you're a vegetarian restaurant and you add pork, that is a hard fork. That is a hard fork because you expanded your menu to add something that wasn't valid under the previous rules. So now it is valid, but anyone who comes to your restaurant who is not aware of this change, a vegetarian, can no longer eat there because you now have pork in your dishes, let's say all your dishes, and as a result, under their vegetarian rules, you are no longer vegetarian. So that's a hard fork. If I'm not told of the change, I can no longer continue to go there because I can't follow the new rules. My rules were more restrictive, and therefore when you open the rules more broadly, it breaks my rules. Now let's look at that same vegetarian restaurant going vegan. Now, if I was a vegetarian who went to this restaurant and you changed all of the menu entries and they're all now vegan, I can still eat there. You don't even need to tell me, because anything that is vegan is also vegetarian, right? You didn't change the rules by adding an element that was previously forbidden. You changed it by forbidding more things But that's okay, because what you're eating now, I can also eat because I'm a vegetarian. So I hope that explains forkology. If you want to watch that video, I go into a bit more detail as to how that applies with consensus rules, but you should get the general idea, and it helps explain it in a very simple term, the way that people can understand. That's the difference between a hard fork and a soft fork. A hard fork is a vegetarian restaurant adding pork and forcing everyone to change their rules or go somewhere else. And a soft fork is a vegetarian restaurant going vegan, where you can keep going there, but it also attracts a more discerning clientele who want a narrower set of choices. The next question is about wrapped Bitcoin in Ethereum. Actually, let's see what else we have, because I see that there are a lot of questions that are not directly related to our permissioned blockchain, and I want to see what else we have here. I think we've covered most of the permission versus non-permissioned blockchain things, and we have time for one more question. All right, let's do this one. Kevin asks, is there a risk that things like Ethereum network could destabilize Bitcoin if enough people decided to transact in Bitcoin using the wrapped form of Bitcoin? Will this have any negative effects on the Bitcoin network, as these transactions are now taking place on the Ethereum network rather than the Bitcoin network? All right, what is wrapped Bitcoin? Wrapped Bitcoin is basically, I think the best way to explain it is a collateralized stablecoin that is pegged to the price of Bitcoin, or to the value of Bitcoin, that allows you to transact on Ethereum with tokens, ERC20 tokens, that represent Bitcoin amounts that you've locked on the Bitcoin chain against that wrapped Bitcoin. It's collateralized stablecoin. Just like DAI is a collateralized dollar stablecoin, wrapped Bitcoin is a collateralized Bitcoin stablecoin. That's basically what it is in a fundamental term. It's a pegged token. No, it doesn't have any negative effects on the Bitcoin network. In fact, what it does is it allows you to make a trade-off. What you're trading off there is you're getting potentially a greater degree of scalability, because the Ethereum network can process slightly more transactions than Bitcoin. And in result, you get a reduction in security, because you're moving from an environment that has very conservative development and very limited evolution of its smart contracts to an environment that is under rapid and continuous change, which means that your platform risks have increased. So now you have the risk of the EVM having a bug or changing, the risk, which is much more open exposure, attack surface area. And the risk of the wrapped Bitcoin smart contract, an ERC20 contract, and all of the other things that are happening, added on to the risk of the collateralized Bitcoin you have on the Bitcoin chain, versus just the risk of the Bitcoin chain. So you've increased your risk by exposing yourself to these additional risks that come from the platform, from the Ethereum platform. And what do you get in return? Well, you got the flexibility of participating directly in DeFi without converting your currency from Bitcoin to Ether. Personally, that's not a trade-off I would make, but my experience is not a universal experience, and my risk model is not a universal risk model, and my choices are not universal choices. So therefore, from my perspective, I would just convert Bitcoin to Ethereum, to Ether, and then use Ether. But there are some reasons why I can see that. If you think that Bitcoin's value as a long-term store value is better, then you want to be able to use DeFi in that environment without risking the greater volatility of the price of Ether and still keeping the value of your Bitcoin in Bitcoin. But again, that comes at an increase in risk, and that may be a trade-off that's worth it for some people. I don't see this as having negative effects on the Bitcoin network per se at all. It's simply a different use case. It's no different than taking your Bitcoin and putting it on a lending market with a custodian like BlockFi or Salt, because you earn some extra interest, but you maintain your Bitcoin, your underlying Bitcoin value by increasing your risk. It's no different than collateralizing something else with your Bitcoin. And it's no different than using, let's say, rootstock or liquid, except that the risks are different, and in some cases the magnitude of the risk is different. But again, that's something that is very difficult to evaluate from an objective perspective. And I think that covers everything we had. So let me just quickly check if there is any follow-up. Yeah, I think I've covered all of the questions. That's it for week 6 of the massive open online course, semester 15 for the University of Nicosia's master's degree in digital currencies. I'm your teacher, Andreas Antonopoulos. Thank you so much for the excellent questions and conversation and follow-up. And thanks for hanging out with me on this wonderful Thursday and going through all of these questions. Next week, we're talking more about consensus algorithms. In week 7, we're going to talk about various other blockchains, including Mimblewimble and things like that. So more on this topic. We're going to cover some of the things we covered today again next week. If you have more questions, if you have follow-up questions, or if I didn't answer one of your questions today, don't forget to ask them again for next week's session, and I will see you in 1 week's time. Thank you so much. Have a good one. Bye-bye.